In this video, we're going to cover the topic of enthalpy. Enthalpy is one of the most important topics in all of thermochemistry and thermodynamics. You guys are going to need your notebook, you're going to need something to write with, you're going to need a calculator. You will not need the thermodynamics table right now. I'm going to give you all the values you need for the video, but you will need to have the thermodynamics table printed out before you come into class. Okay, enthalpy. Enthalpy is basically a derivation of the internal energy equation. So enthalpy is equal to internal energy plus pressure times volume. Or the other way we're going to say it is that the change in enthalpy is equal to the change in internal energy plus P delta V. So now remember, change in internal energy is equal to Q plus W. And we also remember that W is equal to negative P delta V. Right? So what we're doing here is we're basically taking internal energy, which is heat plus work. We're subtracting out the work, right? The reason why we're doing this is because the work that's done on a system or by the system is dependent on the path that you take. Now, the really important thing about this is that since we have Q plus W and then we're subtracting out W, if we're working at constant pressure, the enthalpy change of a reaction is equal to the heat absorbed or gained by the reaction. Right? So delta H is equal to Q if you're working at constant pressure. Now, for our purposes, this usually isn't going to be a problem because most of our reactions are going to take place in open atmosphere. So we're working at 1 atm constantly. And there are a few different ways you can go about calculating it. So you can calculate it by using stoichiometry. So if I gave you the enthalpy of an equation, and then I gave you a number of moles of something, you can then go through and use delta H as a conversion factor in a stoichiometry problem. You can use thermodynamics tables, enthalpy of formation values, we'll get to a little bit later. You can use bond energy tables as a way to do it using that, and we'll cover bond energy a lot more in depth when we talk about chemical bonding. You can do it with Hess's Law. Hess's Law is basically trying to add up multiple different equations. We'll go through that a little bit in this video. And then calorimetry, which, like I said, is our experimental method for determining enthalpy. We're going to do an entire lab where you're going to determine the enthalpy of reaction for a bunch of different substances dissolving in water. So what we'll start off with is we'll actually start off with bond energy. We won't do a problem with this, but I'll just show you the generalized equation. So the enthalpy of reaction is equal to the total sum of the energies of the bonds you have to break. So the bonds you have to break are the reactants. And then you subtract out the energy of all the bonds formed, which is products. Right, and you can go into bond energy tables and do it this way, and we'll go over a bunch of examples of this in class. The one I really want to go over here is the thermodynamics table method, which is using something called enthalpy of formation. The enthalpy of formation, or delta H of F, is the enthalpy change of the reaction when you form a substance from its elements in standard state. Right? So, for example, the enthalpy of formation for, let's say, H2O is the enthalpy change for forming water from O2 gas and H2 gas. Right, so elements in standard state forming the compound or the substance that you're working with, that's enthalpy of formation. Now, one of the things that we're going to look at is that enthalpy of formation for any element in its standard state is 0. Right, so any element in its standard state is denoted by the little degree sign, and all that means is 298 Kelvin or 25 degrees Celsius, 1 atmosphere of pressure, and if it's an aqueous substance, the solution is 1 molar. Okay, so all you do is you do enthalpy of formation for all the products times their coefficient in the reaction. So N in this case is the coefficient from the balanced equation. So you do that for the products, you add them up, then you do it for all the reactants, you add them up, and then it's products minus reactants. So very important distinction here, and this caused a lot of, shall I say, difficulty on last year's AP exam. If you're working with enthalpy of formation, it's products minus reactants. If you're working with bond energies, it's reactants minus products, right? So we'll do an example of this. I want to do the enthalpy of reaction for the combustion of methane, which I gave you the equation below, and I also give you the enthalpy of formation values for all the 4 different substances involved in the reaction. What I want you to do is I want you to use the equation we had in the last slide. I want you to calculate the enthalpy of reaction for the equation as it's written. Okay, and the units for your answer, whenever you give me a unit, your units for enthalpy are usually going to be in kilojoules per mole of reactant. All right, so take a couple of minutes to try to get me that answer, and when you have something, pick up the video again and we'll go over it. Okay, so the number that I wind up with for this total reaction is I wind up with an enthalpy change of negative 890.36 kilojoules per mole of CH4. Now we'll go over how we got this. So if you didn't get that number, that's fine. We'll go over exactly how we got this. Right, so for our equation, we're going to do products minus reactants. So our product side, we're going to do enthalpy of formation for CO2 plus 2 times the enthalpy of formation for H2O, right, because there are 2 moles of water in our balanced equation. We're going to subtract the reactants. So the reactants are enthalpy of formation of CH4 and 2 times the enthalpy of formation of oxygen. So we'll plug in our numbers. CO2 is negative 393.5. Water is 2 times negative 285.83 minus enthalpy of formation for methane is negative 74.8, and then 2 times the enthalpy of formation of oxygen. Well, oxygen's an element in standard state, so that's 2 times 0. And then when you evaluate this, you get delta H standard of reaction is equal to negative 890.36. And again, the units for everything are kilojoules per mole of reactant, which in this case is CH4. Right, so that's how you go through and you do this problem. We'll do a ton of these, so you'll get a lot of practice with this. So this is one common way of solving enthalpy of reaction values. Another common way is to use something called Hess's Law. Hess's Law is basically saying if we don't know the exact path to get from A to B, it doesn't matter. Enthalpy is a state function. So what we can do is we can make up a path, right? So we can make up a reaction process, and as long as it totals the final value of the reaction, we can just add up all the different steps and get our answer. Path is completely irrelevant, right? So we're going to choose the one that's easiest to work with. So for example, our reaction right here, this is carbon plus oxygen forming CO2. It doesn't matter if we go directly from graphite plus oxygen to CO2, or if we go from graphite plus half oxygen to carbon monoxide, and then carbon monoxide plus another half oxygen to make carbon dioxide. It doesn't matter which path we get to, because as long as the initial and final states are the same, the numbers will work out. Now what this means is that you're going to have to play around with some equations. So just some general rules. Enthalpy is an extensive value, so that means that it multiplies and divides as you need it to. So if you multiply an equation by a factor, you do the same to the enthalpy value. So if I double an equation, I double delta H. Also, if you reverse the direction of a reaction, you change the sign, so plus becomes minus and so on. So I'll show you an example of how this is kind of set up. So this is still our reaction of methane. We actually know what the final answer should be now. But notice instead of giving you enthalpy of formation values, I gave you 3 different reactions. I gave you carbon plus 2 hydrogens makes methane, carbon plus oxygen yields CO2, and hydrogen plus oxygen yields water. So what you're going to do is you're going to work on manipulating these three equations, so multiplying, dividing, reversing, so that they add up to be the equation that you're given for the overall reaction. So why don't you take a few minutes, try to get an answer to this. You know what the numerical answer should be, so see if you can figure it out, and then pick up the video again and we'll go over it. Okay, so if we look at this, first thing we need to do is we need to kind of get things in the correct locations, right? So here we have CH4 as a product, but in our equation it's a reactant. So what I'm going to have to do is I'm going to have to reverse equation 1, right? So I'm going to reverse equation 1, and if I reverse equation 1, I change the sign of delta H. Equation 2, I have CO2 as a product. I have 1 mole of CO2 as a product, so I'm good there. Equation 3, I have H2O as a product, and I should have it here as a product. But in my equation down bottom, I only have 1 mole of H2O. I need 2 in my balanced reaction. So what that means is that I'm going to have to double the third equation, which means I'm also going to have to double the enthalpy value. Okay, so if we do this on the next slide, I'm going to reverse the first equation. So reversing the first equation gives me CH4 yields C plus 2H2 and an enthalpy value of plus 74.80. Our second equation is good as is. So we have carbon plus O2 yields CO2. That stays as is, so negative 393.50. And then our third equation we had to double, right? So doubling that third equation gives us 2H2 plus O2 yields 2H2O. We double this equation, so 2 times what we were given is negative 571.66. We'll double check our answer. Carbon here and carbon here cancel out. 2 hydrogens here, 2 hydrogens here. So what we're left with is CH4. And then I have a pair of oxygen molecules right here. So 2O2 yields CO2 plus 2H2O. So I have the equation that I should have. And now all I do is I just sum up these delta H values here, and I get negative 890.36. And again, the unit is kilojoules per mole of reactant. And we get the same numerical answer we had last time. Right, so this is an example of Hess's Law. These are a couple of the ways we're going to figure this out. The next video we're going to do goes over calorimetry, which is our experimental method for doing this. So if you have any questions, make sure you write them down, ask them in class. We'll go over them, and I will see you guys next time.